look up at the night sky, and, well, you might assume you're looking at a static painting,
Right.
just stars sitting there.
Yeah, that's the illusion, for sure.
Exactly. But what you are actually seeing is it's a cosmic graveyard. It's a slowly dissolving collection of ancient cities that have been bleeding stars into the void for like 13 billion years.
It really reframes everything, doesn't it?
It totally does. And today's deep dive is going to completely change how you view the galaxy around you. Our mission today is to extract the core insights from this really groundbreaking article. It was published on May 18th, 2026 by CNRS ENSU via technoscience.net.
Right, the new supercomputer research.
Yeah, that's the one. We are diving into how scientists are using some of the most powerful computers on Earth right now to unlock the secrets of these things they call cosmic fossils, which are, structures almost as old as the universe itself.
The contrast here is, it's what makes this research so profound.
How so?
Well, we're taking the raw, incomprehensibly ancient reality of the primordial universe, like the moments right after everything began, and we are analyzing it using the absolute bleeding edge of modern supercomputing.
It's like past meets future.
Exactly. It's this wild collision of a 13-billion-year-old mystery and the technology of tomorrow.
So, to understand the mystery, we should probably first look at the subjects of the research. The article focuses on these structures called globular clusters,
Right.
and the source describes them as incredibly dense spherical groupings containing anywhere from hundreds of thousands to over a million stars, and they're all bound together by gravity.
A million stars in one localized cluster. It's hard to even picture.
Yeah, and they aren't hiding in some distant, unobservable corner of the universe either. The Milky Way alone contains about 160 of them.
Sitting right in our galactic neighborhood.
Right, and when I picture them based on the research, I think of a bustling, impossibly crowded ancient city trapped inside a snow globe, just frozen in time since the dawn of the universe, floating through our backyard.
I love that. The snow globe image captures the self-contained nature of these clusters beautifully.
Oh, thanks. It just helps me visualize it,
It's a great way to look at it.
Mhm.
And if we connect this to the bigger picture, the presence of those 160 clusters in the Milky Way gives astrophysicists something incredibly rare.
Which is?
A direct, uncorrupted window into the early universe. Because they formed 13 billion years ago, they are surviving relics.
Like actual fossils.
Exactly like fossils.
But
By studying the mechanics of these clusters, we are essentially looking at the blueprints of how galaxies first began to assemble.
Okay, but wait, if we have 160 of these pristine cosmic laboratories just sitting in our own galaxy, and we have the James Webb telescope up there right now, why is an article from May 2026 calling this a major breakthrough?
That's the million-dollar question.
Right, we can literally just point a lens at them and look. Why has their history been a mystery until right now?
Well, because observing a structure in the present tells you very little about the mechanics of its past.
Oh, because it's just a snapshot.
Exactly. Telescopes can show us where the stars are today, but they cannot rewind time. To understand how these clusters formed and evolved over 13 billion years, you can't just take a picture. You have to build a mathematical model.
You have to simulate them.
You have to simulate them. And the dynamics of these globular clusters involve a level of mathematical complexity that has, honestly, until recently, broken every computing limitation we had.
Wow.
Yeah. To realistically model a cluster's life, the scientists had to calculate 3 distinct, massive variables simultaneously.
Okay, let's unpack this, because I want to understand what makes this math so, literally impossible. What is the first variable?
So the first is the internal gravity, which requires what physicists call an n-body simulation.
N-body?
Yeah, meaning you aren't just calculating the movement of a million independent stars. Every single star has mass, right?
Right.
Which means every single star exerts a gravitational pull on every other star in the cluster.
Oh.
Yeah. If star A moves a fraction of an inch, the gravitational pull it exerts on the other 999,999 stars changes, which means their trajectories change, which means their pull on star A changes again.
So it's exponential.
Highly exponential. Adding one more star to a simulation doesn't just add one calculation, it adds millions of calculations per simulated second.
And you have to stretch that across a timeline of 13 billion years.
Precisely.
So it's basically like tracking millions of magnetic marbles in a giant bowl, constantly pulling on each other in real time. That's hurdle one. What's the second hurdle?
The second is the external galactic environment. I mean, these clusters do not exist in a void, right?
Right, they're in the Milky Way.
Exactly. They orbit a host galaxy. And a galaxy has an immense gravitational field that constantly tugs at the cluster from the outside.
So there's an outside force pulling on our bowl of marbles.
Yes, it creates tidal forces. Just as the moon pulls on Earth's oceans, the Milky Way's gravity pulls on the edges of the globular cluster. It's constantly threatening to rip stars away from the outer edges.
Geez. So now, our millions of interacting internal marbles are sitting in a bowl that is being violently shaken and pulled by this huge outside force.
You're getting the picture.
I'm already seeing why normal computers would just melt trying to process this. But the article mentions a third hurdle, which is stellar evolution.
Right, the life cycle of the stars themselves.
Yeah, and I struggled with this part a bit, to be honest. I get that stars are born, they burn through fuel, and they die. But how does the internal, chemical life of a star alter the physical gravitational mass of the whole cluster? Mass is just mass, right?
Well, this raises an important point, because the mass is actually not constant.
Wait, really?
Yeah, and that is the secret mechanism here. As massive stars age, they don't just sit there burning quietly, they generate intense stellar winds.
Well, like solar flares and stuff.
Figure. They're blowing huge amounts of their own matter out into space. And when the most massive stars die, they go supernova, violently ejecting the majority of their mass outward at incredible speeds.
Ah. And because that mass is ejected outward, it eventually leaves the cluster entirely.
That's the key right there. When a star goes supernova and ejects its mass out of the cluster, the overall gravitational anchor of the cluster suddenly weakens.
Because there's literally less stuff there to pull things together.
Exactly. The remaining stars suddenly feel less gravity pulling them toward the center.
So the magnetic marbles in our bowl aren't just pulling on each other while the bowl is being shaken. The marbles are randomly exploding, losing their magnetism, and suddenly changing the gravitational balance of the entire million-marble system.
That is exactly what's happening. And scientists were trying to calculate all three of these interacting layers of physics simultaneously.
For 13 billion years of simulated time.
Which is why the hardware couldn't handle the math until, this team developed the Roland project.
Ah, yes. The Roland project. Let's talk about the sheer technological muscle required to pull this off.
It's massive.
Yeah, this international team didn't just write a clever new algorithm. They secured time on the Janzé supercomputer.
Right, operated by Jancy Idris in France.
Exactly. And the computing specs detailed in the source are just staggering. They ran 25 of these massive n-body simulations, burning through nearly 350,000 hours of GPU computing time.
To put that 350,000 hours into perspective, if you tried to run that on a single high-end commercial graphics processing unit, like what you'd have in a really nice gaming PC, it would take nearly 40 years of nonstop calculation.
40 years.
Yeah.
And they were tracking clusters containing anywhere from 250,000 up to 1.5 million stars. But the detail from the article that really stopped me in my tracks was the duration of the peak simulation.
Oh, the long one.
Yeah. The most demanding single run out of those 25 took 400 straight days of computation to complete on the Janzé supercomputer.
It's almost hard to wrap your head around. A supercomputer running at peak capacity, performing billions of intersecting gravitational calculations per second continuously for over a year.
Just to model the lifespan of one cosmic fossil.
It is undeniably one of the most ambitious astrophysical simulations ever realized. And, if you look at the n-body simulation referenced in the Paulo Bianchini video associated with this research, you can actually visualize the output.
I saw that.
You see this dense, glowing core of stars swarming like a hive, constantly vibrating with kinetic energy over deep time.
It looks alive. The way the core pulses and the outer stars drift, it's mesmerizing.
It really is.
So they feed this impossible math problem into the Janzé supercomputer, let it churn for 400 days, and analyze the data. And here's where it gets really interesting.
This is the best part.
Because the output didn't just validate our current telescope observations. It forced astrophysicists to completely rethink the origins of these structures. The supercomputer revealed two major discoveries about the true nature of these clusters.
Right. And the first major revelation fundamentally rewrites our understanding of their density.
How so?
Well, the simulations definitively proved that the clusters we observe through our telescopes today are just the survivors of a profoundly transformed population.
Meaning, if we went back 13 billion years, they wouldn't look like the snow globes we see today.
Not at all.
Hmm.
The data indicates that at their birth, these clusters were vastly denser and much more concentrated than their current forms.
Oh, which links perfectly back to the stellar evolution mechanism we just figured out.
Exactly.
They started out incredibly tightly packed, but as those massive early stars died and went supernova, the cluster lost mass, the internal gravity weakened, and the whole structure physically puffed up and expanded over billions of years.
That's it. We are looking at the stretched out survivors. The physical expansion is a direct consequence of that early mass loss.
Wow.
The tight, compact primordial clusters had to expand to reach the equilibrium we observe today.
Hmm.
And that brings us to the second major revelation for the simulations.
Which involves angular momentum or spin, right?
Yes.
I found this fascinating. The article notes that the simulated data dictates that these clusters must have formed with a massive amount of internal rotation.
Right, because the kinetic movements of the stars we observe in these clusters today, they're relatively subtle.
They aren't spinning crazily right now.
Exactly. But the supercomputer's 13 billion year physical rewind revealed that to end up with this specific subtle movement today, the initial conditions had to be extreme.
Oh, I see.
They were born spinning rapidly, possessing really high angular momentum.
I keep thinking about how scientists reverse engineer this. It's almost like finding a perfectly smooth, round piece of sea glass on the beach.
Okay, I like where this is going.
You can't just look at it and know what it's shaped to be. But if you have a powerful enough computer to perfectly calculate the exact friction of the sand, the force of the ocean waves, and the exact mineral density of the glass, the computer can mathematically reconstruct the exact jagged, sharp bottle it originally broke off from.
That is a brilliant analogy.
So we look at the relatively calm, expanded clusters today, and the Gene-Zane supercomputer tells us definitively, no, to look like this now, they had to be incredibly dense and spinning like tops 13 billion years ago.
The sea glass analogy works perfectly because it highlights the necessity of reconstructing those unseen forces of time. And for the scientific community, these two newly discovered traits, the high initial density and the massive internal rotation, they're vital.
Why are they so vital?
Because they place strict, undeniable boundaries on our models of the early universe. Astrophysicists now know exactly what the physical properties of the primordial gas clouds must have been to collapse and birth these specific, spinning, ultra-dense clusters.
It narrows down the possibilities.
It completely narrows the parameters of how cosmic structures first formed.
So what does this all mean for us? Like, we know they were once incredibly dense. We know they were spinning. How does reverse engineering the ancient history of a star cluster actually apply to the broader mysteries of the universe we're trying to solve right now?
Well, what's fascinating here is that uncovering the primordial past of these clusters holds the key to understanding a totally different cosmic phenomenon occurring today.
Which is?
The creation of massive black holes.
Oh, wow. Okay.
Yeah. The simulations proved that because these clusters were born so unfathomably dense, they acted as cosmic pressure cookers.
Like black hole factories.
Exactly, black hole factories. Because, think about a typical region of a galaxy. Space is mostly empty, right?
Very empty.
So if a massive star dies and collapses into a black hole out in the galactic suburbs, it generally just sits there in isolation. The odds of it encountering another black hole are incredibly low.
Because there's just too much space between them.
Right. But the simulations show that inside the hyperdense core of a primordial globular cluster, the stars are packed so tightly together that when they collapse into black holes, the intense gravity forces them to interact.
Because there's literally no room to avoid each other.
Exactly. The spatial crowding makes isolation impossible. These black holes drift toward the center of the cluster due to their mass, getting pulled into each other's gravitational wells.
And what happens then?
They form binary systems. Two black holes locked in a tight orbit around one another. And as they orbit, they emit gravitational waves, losing energy, drawing closer and closer until they inevitably, violently merge.
Which is exactly what gravitational wave observatories like LIGO are detecting out in the universe right now.
Bingo. The findings from the Roland project provide the physical mechanism. We now understand that the extreme density of these ancient globular clusters makes them the primary engines or factories, producing the massive black hole fusions we observe across the cosmos today.
That perfectly bridges the deep past to current astronomical observations. That is so cool.
It is.
But the article also points to the future of the clusters themselves and like the future of our galaxy as a whole. The simulations allow scientists to watch something called galactic dissolution.
Yes. We discussed earlier how the external gravity of the host galaxy, like the Milky Way, constantly tugs on the cluster.
Right, the tidal force is shaking the bowl.
Right. Well, the simulations modeled this tidal force over 13 billion years, showing how clusters continuously leak stars.
Leak them.
Yeah, the stars on the outer edges of the cluster are slowly stripped away by the galaxy's gravitational pull. Over deep time, the cluster progressively dissolves, its stars scattering into the broader galactic disk.
So the clusters are slowly evaporating. The Milky Way is just quietly absorbing them, star by star.
Yes. And by understanding the precise mathematical rate at which these clusters dissolve and deposit their stars, scientists can work backward to reconstruct the history of the Milky Way itself.
Wait, so our galaxy is made of these clusters?
In large part, yes. The galaxy we inhabit today is built from the accumulated wreckage of these ancient dissolving globular clusters.
Man, this has been a truly mind-bending deep dive. Let's trace the path we just took, because there's a lot here.
It's a massive journey.
Yeah. We started with these 160 perfect, ancient spheres of stars floating in our galaxy. We realized that simple observation wasn't enough, so an international team threw a seemingly impossible 400-day math problem at the Johnse supercomputer.
To track internal gravity, external galactic tides, and stellar evolution.
Right. And by running the clock back 13 billion years, we discovered that these clusters started out as hyper-dense, rapidly spinning engines. Engines that not only force black holes to merge, but gradually dissolve to provide the very building blocks of the galaxy we live in today.
The entire Roland project is a profound testament to the evolution of scientific methodology, I think.
How so?
Well, we often think of progress in astronomy simply as building a larger mirror or a more sensitive lens to look at the sky.
Just zooming in further.
Yeah, but raw observation has its limits. Sometimes, to discover the truth, you have to build a digital universe inside a machine, subjected to the relentless laws of physics, and see what survives.
That's a great way to put it.
We need the multiple perspectives of both the telescope and the brute force power of modern computer science to truly see the architecture of reality.
The telescope shows us what is. The supercomputer shows us how it came to be.
Beautifully said.
Which leads me to one final thought I want to leave you with today. We talked about how the Milky Way's gravity has been slowly stripping stars away from these hyperdense globular clusters for 13 billion years.
Galactic dissolution.
Right. A slow, continuous leak of stars drifting out into the vastness of the galactic disk. So, the next time you go outside on a clear night and you look up at the solitary individual stars scattered across the dark sky, it makes you wonder.
It really does.
How many of those lonely stars you're looking at right now are actually long-lost escapees, refugees from a bustling, spinning, ancient cosmic city that has been slowly dissolving since the very dawn of time? Keep looking up and keep asking questions.